these are the important terms that you have to have an idea when you are taking the decision and calculating or in the decision process. So, size of a test. So, it is the maximum probability of committing type 1 error. So, I said that type 1 error is the most critical error. So, size of a test means maximum probability of committing type 1 error, which means rejecting the null hypothesis when it is actually true, and the level of significance. So, level of significance is denoted by alpha and the maximum probability of type 1 error that the researchers can bear. So, it is denoted by alpha, and most of the time it is 1%, 5%, and 10%. So, those are the three values that we have used frequently as researchers, but you can have many different values in your own experiments according to your situation, because it is the researcher who decide the value of alpha or the level of significance. A test is conducted keeping the size of the test is equal to or less than alpha but closer to alpha, which means when we are conducting the test, we take a value for alpha which is equal to the size of the test or less than but closer to the size of the test. And the confidence coefficient. Confidence coefficient means 1 minus alpha. And beta risk or beta is the probability of committing type 2 error. So which means accepting H naught or do not reject H naught when H naught is false. So that is the type 2 error, and the probability of type 2 error is beta. And the power of a test means 1 minus beta, or the probability of rejecting the wrong null hypothesis, which means power means the probability of rejecting the null hypothesis when it is false. So that is making a correct decision. Now, p-value. So corresponding to an observed value of a test statistic, the p-value is the lowest level of significance at which the null hypothesis could have been true, which means in the process we have to calculate a value of a test statistic using the distribution, and that is the cutoff value which help us to take the decision. So for the convenience, we can calculate the probability that particular observation from this distribution is greater than or less than to these critical points. So that is the probability. So in the diagram, we can have a clear idea about this p-value and its rejection region. So rejection region is the subset of values of the test statistic that are unlikely if the null hypothesis is true. So suppose this is the distribution of the test statistic and this is the critical value. So here we have a parameter value for the hypothesis, and this is the critical value, which means if our sample estimate gives a value or we gives an estimate for this parameter and it is greater than this one, it is somewhere in here, we can say that we have to reject this null hypothesis. So I can demonstrate it like this. Suppose this is the distribution of our test statistic. So this is theta naught, and my H naught is theta is equal to theta naught. So this is about the population parameter, and I need to check whether this is true or false. If this is equal to theta naught, so then we are sure that our theta is in this point. But if it is not, so then it is in somewhere here or it is in somewhere here, which means it is a 210. So theta is in here or in here. But we can't say that we are taking a sample. So depending on one sample, we can't say that uh, if our sample estimate for theta is not equal to theta naught, then our S naught is false, because we can have an estimate in here or we can have an estimate in here. So this gives, or this value is given from one sample and this value is given from another sample. But still, if we increase the sample size, we can have a value more closer to theta naught. So this is our hypothesized point, but we can have some closer values to this point and still we can accept that value. So, but when we are moving to this tail or the lower tail and to the upper tail, the points in here, they are highly, so they are unlikely to occur, which means the probability of occurring this point and this point, or the points in here or in these two tails, are unlikely to occur or have a low probability to occur. Then we can have a critical value, which means a value which helps us to take the decision. So this is C1 and this is C2. Now suppose we need to take a decision. So we calculate the value of theta or theta hat, estimate of theta from our sample, and that value is less than C1 or that value is greater than C2. So then we can consider that these values are sufficiently far away from theta naught. So we can reject H naught. But if that value is in here or in here, which means between C1 and C2, we can't reject the H naught. So that is the process of making the decision. So if our estimate of the test statistic is on this region or in this region, we can reject the null hypothesis, which means this area and this area is the rejection region, and any other value between these two is an acceptable value. So though they are not exactly equal to theta naught, we say that still we can conclude that theta is equal to theta naught. For an example, if we can go back to this one, average case, so suppose this is the sample distribution of averages, and we say that it is 368. Now we need to test it. So we take a sample and my sample value is 365. From the techniques we are discussing in the upcoming sections, we know that you might know C1 is theta, or C1 is less than theta naught. So this is now mu naught, and this is my first critical value. It is 340 and 380. So if I got a sample mean which is greater than 380 or less than 340, I can conclude that this is wrong. But if I take a sample mean which is in between 340 and 308, though they are not exactly equal to 360, we can conclude that mu is equal to 360 because we are taking samples, we are not examining the entire population. So that is the sample value. So we don't want it to be exactly equal to 368, but if it is in the sufficient distance from 368, we can consider that our H naught is true. So the process of hypothesis testing means calculating these values first, and then using the sample we calculate this and check whether it is in the acceptance regions or rejection region. So these are rejection region for two-tailed test. And now suppose we have one-tailed test. So this is the distribution and it is bit skewed, and here we say that for this one, suppose this is the average direct cost is less than 40. Now this is 40. So we say it is in H naught, we say it is less than, or in H1 or alternative hypothesis it is less than 30, which means the actual value of this parameter, average value, should lie on this region. But on our H naught, we say that it is greater than or equal to 40, which means suppose if H naught is true, always we take the decision by assuming that H naught is true. If H naught is true, then the value of the average is a value greater than or equal to 40, which means it can be 40 or any other value in here, here, here. So we don't know. Suppose if it is 40, so this is the distribution. If it is this one, 50, so then the same distribution and it is moved towards this. Now middle of the distribution is 50. If the average cost is greater than or equal to 40, which 50 is greater than, so now our H naught is 2. And if it is 60, then this distribution move to this side, and now the middle of this distribution is 60. So you can see that previously, so at the beginning, or the least value that we can take to the average is 40, and any other value which is greater than 40 can be accepted if H naught is true. We don't know the actual value, but we know that if H naught is true, then this distribution, or the middle of this distribution, moves toward this side, which means the tail. Previously it was here. This tail now move to this place, which means with the increment of the value mean, tail moves to this one. So the values in this end or the lower tail are less likely to occur. Then we can conclude that this is the critical value. So which means if we can find a value equal like k, we don't know the value of k. So in this process, we have to find the value of k. So we can write down it as k, and using the distribution information, we can find the value for k. Now we take a sample, and our sample mean is somewhere in here. Suppose it is 56. So then we can say that our S naught is true because it is, we assume that our S naught is true, and from the sample we take 56 as the estimate for the mean, so we can consider it as true. But if we take a sample and it gives a value like 25, now it is a value less than or equal to this k, which means this is value of the test statistic or the critical value, and it is less than this one, which means if S naught is true, our middle is in this range, and a value beyond this point is less likely to occur, and we assume at the time we are assuming that our S naught is true. So depending on that assumption, having a sample which gives a mean which is less than this k, we can take a decision that our assumption is wrong, which means we have taken a sample, and that sample have returned a value that has a probability or very low probability to occur. So then we reject H naught, and we say that we do not have enough evidence to uh, accept H naught, or we basically we say we reject H naught. But if we took a sample and it gave a value like this, or even a value in here, it is greater than 40, or not 40, it is greater than k. So if our sample gave a value somewhere in here, still we can say that our S naught is true, which means we don't have enough evidence to reject S naught. Depending on this sample, we can reject S naught because it gives an average value greater than k, which means this is the rejection region, and if our sample value lies on the rejection region, we reject H naught, and if not, we accept H naught. So this is for less than type alternative, and if it is a greater than type alternative, so it is like this, and our alternative is greater than, which means our null is less than. So by moving to this, suppose first this is uh, 2500, example 2. So our null is less than or equal to 2500. So if our S naught is true, so then the actual value of H naught somewhere in this region, which means this distribution moves towards this side, and the values in this area is less likely to occur. So we can have critical value, and we can find the value of this one first using the information of this distribution. And we take a sample, and if our sample gives a value in here, it is less than k, which means we can't reject the S naught, we have to accept. Or if it give a value, no problem, we can accept the null hypothesis. But if our sample gave a value here, which means greater than this k, since this is the rejection region, once we get a value which belongs to the rejection region, we have to reject the null hypothesis. So this is the uh, rejection region. So that is how you can identify the rejection region. And that probability or p-value is like this. Suppose for the same example, so we know, so we are assuming that this is the distribution, and if H naught is true, so the greatest possible value for mu when H naught is true is 2500. So we take this distribution, and our calculated value or our estimated value is somewhere in here. It is 200 or 2600. Now, using the information of this distribution, we can calculate the probability that this uh, the probability of mu is greater than 200 or 2600. So this is the level of rejection or the probability of rejection. So if this value is less than alpha, which means we can consider that this probability is less than the probability of type 1 error, which means the size of the test. So then we can reject. But if it is greater than alpha, so still we can consider that we don't have enough evidence to reject this H naught. So that is the basic idea about hypothesis testing in graphical.